grab your 5-4 notes. And today we are going to review a lot of the stuff that we went over last year and add in some new stuff as well. So, first slide says that the inverse of a relation consisting of the ordered pairs x and y is a set of all ordered pairs y and x. And the notation is f of x, f negative 1 of x, which represents the inverse of f of x. So when you have an inverse, you can see whether it's a function by doing a horizontal line test, or you can do a vertical and a horizontal line test on the original graph to tell whether it is a 1-to-1 function. If the function is a function and its inverse is a function, that is considered a 1-to-1 function. So on here, determine which function is 1-to-1. So the first one, these are all functions, but the first one does not pass the horizontal line test, so its inverse is not a function, making it not a 1-to-1 function. This next one, which is a line, is a function. It passes the vertical line test as well as the horizontal line test, making it a 1-to-1 function. So yes, this is 1-to-1. This last one would not be 1-to-1. Inverses graphically are reflections of each other over the line y equals x, which is called the identity function. So over the line y equals x, if it's a mirrored image on either side of that line, then it would be considered a function. So this graph is just an example of f of x and its inverse g of x, and that they are graphically inverses because they reflect over the line y equals x. So to graph the inverse of a graph that is a piecewise function like this, you would just use y equals x to inverse the points. So first I'm going to list all the points that are on here, and then I'm going to switch the x's and y's and graph the inverse of them. So my original points are -4, -2, -3, 3, 1, -1, 3, 0, and 4, 4. Then the inverse of those points would be the x's and the y's switched. So the inverses of my points would be -4, -2, -4. -3, 3, -1, 1, and 0, 3, and 4, 4. So when I graph these points, I'm going to graph them in order and connect the dots as they go. So -2, -4 would be down here. -3, 3, not -3, 3. That should be 3, -3. Sorry. 3, -3 is over here, so I connect those. -1, 1 would be right here. 0, 3 would be here. And 4, 4 would be over here, which gives me a graph that reflects across the line y equals x. So if I folded it on the y equals x, then that would give me the same graph. So then we're just going to, we are going to find the inverse of equations, and the way that we do that is, I skipped a slide, is we change the f of x to y, interchange x and y, and solve for y, then change your new y to be f -1 of x so it has the correct notation. Feel free to pause this video at any time during this lecture so that you can take a minute to review what I'm talking about or finish a problem if you want to. So on this first one, f of x is really y, so y equals x squared plus 1. then I would switch the x and y, so it becomes x is equal to y squared plus 1, and solve for y. So subtract 1 from both sides, giving me x minus 1 equals y squared, and then taking the square root of both sides. I have to add a plus or minus when I take the square root. So y, which is really f negative 1 of x, which represents my inverse, is plus or minus the square root of x minus 1. So plus or minus the square root of x minus 1 represents two separate functions, but you have to have both of those functions in order to get the actual inverse. So if I were to graph both of those functions and my original, and I go to y equals, clear both of those out, I had x squared plus 1, and my inverse was, one of them was positive square root of x minus 1, and the other one is the square root of, negative square root of x minus 1. So I have to put them both separately because they're both individual functions, not a whole function. But when it graphs, there's my original function, and then there's the inverse of it. So it has to have both pieces to be the complete inverse of my original function. And that way it shows the actual inverse, not just half of the inverse. Okay, on my next one, this one's a new type of problem. So the rest, that one I just did should be a little bit of review from last year. But this one's a little bit different. So the g of x is really y, so I'm going to interchange my x's and y's, which would make it x is equal to y plus 1 over 2y plus 3. So now it's like what we've been doing, and we need to get a common, well, we figure out what our common denominator is, which is 2y plus 3, and then multiply both sides by that common denominator. When I do that, my 2y plus 3 on the right side gets canceled. I distribute my x on the left side and end up with x, 2xy plus 3x is equal to y plus 1. This is where it gets kind of weird. I have two y's and they're not like terms, but I still need to get them on the same side if I'm going to solve for them. So I'm going to subtract y from both sides, which would give me 2xy minus y plus 3x equals 1. And then subtract 3x from both sides, because then I have 2xy minus y is equal to 1 minus 3x. At this point, I can factor out a y from the left side, which would leave me with y times 2x minus 1, which is equal to 1 minus 3x. I factor out the y so that then I can divide by 2x minus 1 and get y by itself. So I divide both sides by 2x minus 1, and my 2x minus 1 cancels on the left side, leaving me with y, or g negative 1 of x, equal to 1 minus 3x over 2x minus 1. So this is part of my answer. The other part are my restrictions, my excluded values. So my excluded values for my answer is x is equal to 1/2. However, I also need to include the restrictions from the original problem. So my original function, the excluded value should have been x could not be 3/2, negative 3/2. So I have to include that in my solution. So any restrictions that or excluded values that a function starts with need to be included in the inverse. They are called inherited restrictions. Okay, so I would maybe pause right here so that you can try these ones on your own before you check them with what I get. So if I'm going to do these, I would replace that with y, then interchanging x and y, making it x equals 2y cubed plus 3. Then subtract 3. X minus 3 is equal to 2y cubed. Divide both sides by 2. So I would have x minus 3 all over 2 is equal to y cubed. And then I need to take the cubed root of both sides, to get rid of the cubed on my y. And you can just leave it like this. So y or h negative 1 of x, because that's our notation, is equal to the cubed root of x minus 3 all over 2. This does not have any domain restrictions because there are no x's in our denominator, so it makes it nice. The second one, we're going to do a similar thing with. So this is really y, which then becomes x is equal to the cubed root of y minus 3. Add 3 to both sides. X plus 3 is equal to the cubed root of y. And then to get rid of a cube root, you cube both sides. The cube undoes the cubed root, leaving you with x plus 3 cubed is equal to y, or g negative 1 of x. You do not need to expand that function. Okay, so this is also a new one. If we were taking the square root of something, we cannot take the square root of a negative number and end up with a real number. So, inherited restrictions is talking about our restrictions from our original function. This is our original function, and the inherited restrictions means that 2x minus 3, or anything under the square root symbol, must be greater than or equal to 0. If I solve this for x, I would get x has to be greater than or equal to 3/2. This is technically your domain and must be included with the inverse function as well. So now I'm going to do what I usually would do and find the inverse. So I would have x equals the square root of 2y minus 3. Then to get rid of the square root, I would square both sides, which would give me x squared is equal to 2y minus 3. Add 3. X squared plus 3 equals 2y. Divide by 2. So y, or f negative 1 of x, is equal to x squared plus 3 all over 2. With the domain restriction, x has to be greater than or equal to 3/2. I would also pause at this point and try this one on your own. And then after maybe 5 or 7 minutes, hit play again and see what we got. So our initial domain restrictions are 2, is just 2. So you only have domain restrictions when you have an x in your denominator or when you are taking the square root of something. So if x cannot be equal to 2, I'll leave that alone for a second and then solve how I usually would. So I need to change this to be x equals 4y plus 1 over y minus 2. And the common denominator between both sides is y minus 2. So I'm going to multiply both sides by y minus 2. And that will cancel on the left side or right side. And I would end up with xy minus 2x on the left side. And then 4y plus 1 on the right side. I then want to get all my y's on the same side, so I'd subtract 4y, and I'd add 2x to get rid of that. So I would be left with xy minus 4y equals 2x plus 1. I then am going to factor out a y from the left side, leaving with x minus 4 in parentheses is equal to 2x plus 1, and then divide both sides by x minus 4. So my final answer, which in inverse form would be f negative 1 of x, is equal to 2x plus 1 over x minus 4. And my domain restriction here is x can't be 4, but I also have to include the inherited one from before, and x cannot be 2 either.